Hey, afternoon, everybody. Welcome back to another round of astronomy, and yeah, we'll just keep going here. Now, to continue on for the discussion for today, we're going to move ahead and talk about stellar evolution. That is to say, what does a star do now that it's on the main sequence? What happens? And furthermore, what happens when it starts dying? In other words, leaving the main sequence, becoming a giant, a supergiant, and eventually coming back down here to a white dwarf. We'll have to introduce some new ideas. First of all, I'll mention right away the mass of the star will determine its final fate. So, low mass stars, medium mass stars, high mass stars, and for lack of a better term, really high mass stars, those will all have different endpoints because of their mass. Mass determines everything. We'll have to introduce a new idea, shell fusion. Okay. So this is in contrast to the core fusion that we've already discussed. We'll have to introduce a new idea. And then talking about different fates of stars, in addition to these white dwarfs, we'll also have to discuss what does it mean for a supernova to occur. These tend to be the high mass stars. And coupled along with that discussion, we'll talk about a new category or classification scheme. And then lastly, of course, my personal favorite, the one that's really cool, black holes. So we'll try to get into that idea and see where we go from there. Okay, let's get cracking. So I have a question for you, first of all. Here it is. Willy Wonka is downsizing his workforce. And the question is this: to maintain the same rate of candy production, the remaining Oompa Loompas must, go ahead, take a minute, think that over. So, in this sense that if you decrease the size of your workforce, but you're trying to keep the same production, the workers that remain must work harder. You've got less hands that have to do the same amount of work. That means that people have to work harder. Okay? Now, we're going to use the same idea here, except now we're going to apply it to stars. So here's the next question for you. So as a star ages, in other words, we have a star that's on the main sequence. You can think of our sun, for example. As a star ages, what can you tell me about the number of atoms in the core? And remember, I'm thinking the core is the part of the star that's undergoing nuclear fusion. So go ahead, take a minute here, come up with an idea. Okay, good. Hopefully, first of all, we have to remember the fusion process. And the fusion process says we take 4 hydrogen atoms and we combine it into a single helium atom with a little extra energy. Okay? So the number of atoms in the core, the part of the star responsible for fusion, continually decreases. Here's the next question for you. If the core of a star were to stay the same volume, so let's say for a moment that while we're doing the fusion process, the core stays the same size, just momentarily. So if the core of a star were to stay the same volume, but you're decreasing the number of workers, okay, tell me, what would happen to the fusion rate? Got it? I guess the other way we could say it is, what would happen to the density if the volume stays the same, but the number of hydrogen atoms available decreases? You could say that the density of the core will decrease. And because the density of the core decreases, what happens to the rate of fusion? It will also decrease. Cool, huh? And now we can start applying our ideas. Let's say, okay, so if the volume stays momentarily the same, the rate of fusion is now too low, right? The density has decreased. That means the rate of fusion has decreased. It's too low. And so what will happen is the core will collapse in order to increase the rate of fusion. So, that said, we have decreased amount of hydrogen in the core. And because of that, the fusion rate is too low. And to compensate for that idea, because the density is too low and the fusion rate is too low, the core will compress in order to increase the fusion rate. Now, to think about this, that the number of workers in the core, the number of hydrogens, there's less of them, which means the remaining ones need to, quote unquote, work harder. In other words, perform the fusion process faster. What happens to the temperature of the core if the rate of fusion is increasing? The temperature goes up. And what happens to the outer shells if the temperature of the core goes up? Temperature of the outer shells goes up, which means the physical size of the star increases slightly. So, as fusion goes on in the center of our star, the core is continually contracting, which means the core temperature is actually increasing, which means our star is slowly growing. And this is a general rule of thumb, one that we'll actually take advantage of quite often, is that as the core shrinks, the outer layers expand. As the core grows, the outer layers will shrink. Now, you could think of the sun as being the canonical example, but off the main sequence, how do we retire? And the key piece here is, let's think about what got us onto the main sequence in the first place. How do we know that we have a star? It's if fusion is occurring in the core. So how a star moves off of the main sequence is when core fusion stops, when it can no longer fuse hydrogen in the core. That's when we leave the main sequence. That's when a star is officially retired. You might say, well, why does that happen? Why would a star get off the main sequence? And we already talked about this. It's that it runs out of gas. I'll phrase it a little bit differently here. I will say that the fuel that the star has is dirty. If you put dirty gas into your car will not work. A star, after its lifetime, has a dirty gas tank. It can no longer continue the core fusion process. You say, where does that come from? Where does the dirty gas come from? From the star itself. Okay. So a main sequence star has this nice core hydrogen-hydrogen fusion process going on. I'm using the yellow to represent a portion of the star that does not do the fusion process. Okay. Now, for simplification purposes, you can think that as this hydrogen process continues, you slowly form additional helium in the core. And that's what that red dot's supposed to represent, helium. So the fusion process itself produces helium, which does not participate in future fusion processes. So that's what stops a star from continuing on. When about 10% of the core is helium, the fusion reaction can't be self-sustaining. The star is officially done. Okay, let's keep going then. So parting ways. Here is where we have to actually make the distinction between low, medium, and high mass stars. Okay. Now, low mass stars, the protostars, I called them the never-weres. When they're less than about 1/10 of a solar mass, they are not able to start hydrogen-hydrogen fusion in the core. So that's why we call them brown dwarfs, but they're technically not even a star. They never had fusion going on in the core. The reason for that is that the gravitational collapse of the star is not sufficient to obtain temperatures high enough to do the hydrogen-hydrogen fusion. You need about, I'll round it and say 10 million Kelvin. When you get to temperatures of about 10 million Kelvin, you can do a self-sustaining fusion reaction in the core. So it's just, they're too small. They don't have enough mass. We will play the same song and dance for low mass stars. Low mass stars between 0.1 and 0.4 solar masses, they will go and use up most of the hydrogen in the star. They will do the fusion process. But the issue is that they are not massive enough to fuse helium. Think about, after the star uses up all of the hydrogen, that star will start to compress. The fusion turns off. Okay? The star will gravitationally collapse. It will start getting warmer, admittedly, but it will gravitationally collapse, but never hit 100 million Kelvin. It doesn't hit a high enough temperature to start the helium-helium fusion process. Stop. The gas tank is empty. There is no, do not pass to go. Do not collect $200. You are done. What we are left with at the end of the day is a very hot ball of helium. A very hot ball of helium. This will sometimes be referred to as a helium white dwarf. So let's keep going. Now I have to introduce this idea of shell fusion. So imagine for a moment that we're dealing with a medium mass star. It gets a dirty gas tank, and so the helium in the core does not participate in the fusion process. However, well, you can start, the first thing we can think about is that the hydrogen core fusion stops. Now, because that fusion in the core has stopped, the temperature of the core will drop and the star will start collapsing, start compressing. Because the star is compressing, gravitational collapse of the star, the temperature will slowly increase. And now here's the cool thing. A shell of fuel surrounding the core that's able to ignite. So we have the hydrogen-hydrogen shell fusion take over. The hydrogen that is involved in the fusion process has to work really hard. The fusion rate is astronomically huge. Because of that fusion rate being really high, the shell temperature is very high, and the outer layers expand even further than what they used to be. You end up with a ginormous star, or a giant. So the supergiants and the giants that we see in our HR diagram are typically stars that are undergoing a hydrogen-hydrogen shell fusion process. It's because there's a smaller volume in the star that is doing the fusion, and therefore the fusion rate in that area is huge, which means that you have a huge temperature and then the outer layers expand. I've already mentioned this, but for the sun, when the sun hits the hydrogen-hydrogen shell fusion stage, it will expand out to roughly the orbit of Mars, 1.5 astronomical units. The last thing I'll note, you'll say, but wait, Greg, wait a minute. Why we have this hydrogen-hydrogen shell fusion process occurring? Why doesn't the gas in this hydrogen-hydrogen shell also get dirty? And I say, exactly. While this hydrogen-hydrogen shell fusion is going on, you are generating more helium. And for simplicity, I will say that helium that gets generated is added to the core. So we are in the shell fusion stage, and we're adding helium ash to the core. What does that mean? That means that we're packing more material into the same volume. The density of the core is slowly increasing. Now, if we're thinking about this random process again of atoms in the core walking around until they bump into the right atoms to fuse, we're increasing the likelihood of two helium atoms smashing together and starting the fusion process. What we have to do is simply wait long enough for enough shell fusion to occur to add enough helium to the core, and eventually we're going to start core fusion again. The issue is that it's not going to be hydrogen-hydrogen. It's going to be helium-helium. And that point when that occurs, when there's enough helium in the core so that the density is high enough so that helium-helium fusion takes place in the core, we call that the helium flash. What happens to the temperature right after it starts the fusion process again? It jumps up. There's a huge increase in the temperature. So now you have fusion going on in the core. The temperature has gone up. What does that do to the hydrogen-hydrogen shell surrounding the core? If the temperature of the core goes up, the temperature of the shell layer goes up. But then here's the trick. Here's where we have to be careful. If the shell temperature goes up, and I'm talking right now about the hydrogen-hydrogen shell, if the temperature of that shell goes up, what happens to the physical size of that shell? It expands. And if the physical size of that shell expands, what happens to the fusion rate in that shell? It goes down. The fusion center of the star expands, and because of that, the temperature of the outer layer actually drops, and the star gets slightly smaller. If you've got this, and I say pause here, go back and review the last half an hour, but if you've got this, then you're ready to go for the rest of this. Now, I'll say, what happens next? Say, rinse, wash, and repeat. And what do I mean by that? Well, let's take a medium mass star like our sun for a moment and think about what's the next logical step. Well, the helium-helium fusion in the core produces impurities like carbon and oxygen. So that helium-helium core fusion will present impurities in the gasoline. Eventually, the core fusion of helium will stop. And now we rinse, wash, and repeat. When the helium-helium fusion in the core stops, the star will start collapsing. The density of the hydrogen-hydrogen shell will increase, which means the fusion rate of the hydrogen-hydrogen shell goes up, and I'll have an expansion of the outer layers. The fusion center shrinks because the helium-helium core fusion has turned off. So the fusion centers shrink, the outer layers expand. And now what happens? Well, the hydrogen-hydrogen shell fusion adds additional helium to what I will call the helium shell. And if it adds enough helium to the helium shell, the helium fusion will turn back on. Okay. I'll call that a reflash, or reignites, another helium flash. And of course, again, because the helium process has turned back on, the core will the fusion centers will expand. Because the fusion centers have expanded, the outer layers of the star will actually physically contract. Now, here's the last important point. I'll say every time you have a helium flash, you will have some material ejected out into space. This is a huge explosion, right? You're restarting the fusion process, and you have a tendency of blowing some of the outer layers of the star out into space as solar wind. And now here's where the rinse, wash, and repeat part comes in. The helium-helium shell fusion produces additional impurities. Eventually, the helium-helium shell fusion will turn off. The hydrogen-hydrogen shell fusion will have to pick back up. The star expands. Enough helium gets added to the shell. Helium shell fusion again begins. Another ignition. Runs out, turns off. Hydrogen-hydrogen shell fusion takes over. Reignites, turns off, etc., etc. So now we have our Groundhog Day kind of loop going on here. Okay. Now let's go ahead and look at some pretty pictures. You're like 8 weeks in, we finally get to look at some pretty pictures. And this is where the title on my slide comes in. I say the Emperor's Clothes. What will happen during this helium flash process is you are slowly stripping away layers of the star, which gives you something like this. You have the Cat's Eye Nebula, Hourglass Nebula, Eskimo Nebula. Oops, excuse me. What you're looking at are various stars undergoing this helium flash process. And every time you have a helium flash, you eject layers of the star out into space. This process can actually eject up to 40% of the star's mass just out into space. This, first of all, gives us some very pretty pictures, but in addition to that, that material turns into clouds of gas, which can be incorporated into new stars and or planets. Right? What was our ingredient list to form a star in the first place? A cloud of gas. What we have during this helium flash process is a star producing a new cloud of gas. It's cosmic recycling. This is awesome. Okay. But wait, there's more. Okay. So let's walk through our HR diagram. I said our HR diagram gives us an idea about the birth, life, and death of stars. So we've already talked about our run-of-the-mill stars find themselves on the main sequence. Right here, hydrogen-hydrogen core fusion. When we leave the main sequence, you notice that we suddenly start having stars leaving the main sequence. This is when we have the hydrogen-hydrogen fusion turning off in the core, but rather hydrogen-hydrogen shell fusion. Sometimes we refer to this as the red giant branch, because the physical size of the star has increased dramatically. Next, you notice that right up here, there seems to be a spot where no stars progress beyond. That's because once the stars reach these locations, this is where the helium flash occurs. Okay. So now we have helium-helium core fusion going on. The physical size of the star shrinks, and so the luminosity is going to go down. And conversely, the physical size of the star shrinks and the temperature increases. So we end up getting a trade-off and the luminosity goes down slightly. And our stars actually end up right about here. This is called the horizontal branch, and it represents stars that are undergoing helium-helium core fusion and some hydrogen-hydrogen shell fusion. So this is when the core fusion actually initiates. And then as the star kind of settles down into its kind of rhythm, its groove, it ends up here on the horizontal branch. Now, as the helium-helium core fusion turns off, the star will start bouncing back forth between these two locations. That's generally referred to as the asymptotic branch, when you have helium-helium and hydrogen-hydrogen shell fusion going on. Now, for medium mass stars, there's got to be an endpoint. Eventually, you will run out of helium to burn. You will not have enough hydrogen to produce more helium. And so your gas tank is out. You're done. Now, remembering that we blow off a lot of extra layers into space, generally what you're left behind with is a star primarily comprised of carbon. The medium mass stars are not massive enough to collapse and fuse carbon together. So at this point, you've fused all of your hydrogen, you've used up all of your helium, you're left over with essentially a carbon star. Those we refer to as white dwarfs. So I said white dwarfs, but I prefaced it with helium white dwarfs. Generally, when you hear the term white dwarf, it's a carbon star. And so what happens is, because you've removed so many layers of the star, you'll decrease in physical size, but maintain the temperature. What you're doing is you're stripping away the outer layers, and you're eventually going to find the bare core of the star, okay? Right here. So you're making the star smaller and smaller in size, but the temperature is basically the temperature of the core. And so your white dwarfs end up here. Again, they will take billions of years to cool off, but eventually you'll see them drop even further in luminosity and temperature, okay, until you can't see them anymore. So unfortunately, medium mass stars like our sun aren't able to hit the 500 million Kelvin to fuse carbon. Well, how about high mass stars? And here is the best thing. Second best thing. So the first thing is helium flash. Why wait? In the medium mass stars, there is a period where the hydrogen-hydrogen shell fusion has to add additional helium to the core in order to get the helium-helium core fusion to start. High mass stars don't have to wait. When the fusion turns off in the core, the shell fusion will pick up. But the large mass, the high mass stars, are massive enough that they can compress the helium already in the core to get the fusion process to start right away. So I say, helium flash, why wait? We just collapse and start fusing the stuff that's in the core already. It's massive enough to do that. Now here's the best quote. The next stages are easy to imagine in outline, but complex to describe in detail. Okay? What that means is we're going to apply the same kind of thought process, but we don't need to do anything else. So here's the thought process, is that high mass stars are massive enough that, for example, once the gas tank of helium runs out, they are able to collapse and start the fusion process for carbon-carbon. Okay? And if they're high enough mass, say if they're 4 solar masses, they can perform the carbon-carbon fusion process. Okay? If they're over 8 solar masses, then it's once the carbon runs out, they can compress and actually start fusing neon and neon. Or if they're over 8 solar masses, they might be able to fuse oxygen and oxygen. So how massive they are will dictate at what point will they stop fusing. So what you end up with some of these high mass stars is what I promised you at the beginning, gobstoppers. You have a core that might have neon or oxygen fusing, and then surrounding that core will be different shells of various elements undergoing that fusion process. You say, well, where does it stop? No matter how massive a star is, it will never be able to fuse iron. Remember, you don't need to know all of this. I mean, you should know hydrogen, hydrogen to helium, and helium, helium to carbon. Okay? Know those. The other thing that you need to know is that when you hit iron, you are done. It does not matter how massive a star is, it cannot fuse iron and iron in a self-sustaining manner. Iron is the stopping point. You can't go any further. So in the really, really massive stars, you get the iron core surrounded by a bunch of shells, just like a gobstopper. How about time? Let me give you an idea about how long it would take to do these fusion procedures. This leads into what happens when a high mass star runs out of fuel. So take a 25 solar mass star, for example. It takes about, let's see, 10 to the 7th, 10 million years to go through all of its hydrogen, at which point it will pick up the helium-helium fusion process. And that's another million years. After that, carbon-carbon, about 1,000 years. And again, the reason why there's such a dramatic decrease is because you're producing less than the previous step. So if you have hydrogen, about 10% gets turned into helium, for example. Okay? And so that means that you have less helium to do fusion process with, which means it'll take less time to do it. Similarly, carbon, neon, only 3 years. Oxygen, 4 months? Are you kidding me? The time that the semester has gone on, you could use up all the oxygen in a star. And then you notice that the really interesting one, silicon takes about 5 days. Core collapse. What does this mean? After all of the fuel is used up, you're no longer fusing in the core. There's nothing to prevent the gravitational collapse of the star. One of the things that can happen is what's called a supernova. Okay. Sometimes this is referred to as the Big Bounce. I'll have to get a demo out for you. Okay. But let me walk you through it. Imagine for a second that you take a star and you start compressing it and compressing it and compressing it. Okay? Compressing it beyond imaginable almost. In fact, you compress it so much that those electrons in their electron ladder outside of the nucleus start getting compressed so that they have to combine with the protons in the nucleus. And when you take that electron and you press it into the proton, you fuse them together. I'll say fuse them together to form a neutron. And that's the last big hurrah. It's a one-time deal, but that's the last big hurrah for this type of star. Okay? You take a proton and electron, you push them together and fuse them to form a neutron. And in addition to that, you get a whole lot of energy that's released. This whole process, the entire star, takes about 1/4 of a second to do. That's a huge release of energy in a really short time. What that means is that the part of the star gets that energy and explodes out into space. Okay. In fact, about 80% of the mass can just be ejected out into space because of this process. Now, I said, hey, this is a one-time process. taking those neutrons and taking those electrons and fusing them with the protons to form neutrons. That's kind of a one-off. That's a one-time bit. In that process, there is a little bit of alchemy going on. So that's what this table is supposed to show you. What we have here, and I'll highlight the orange and the green, which are not particularly easily distinguished by my eye, are the elements that are generally produced either in small stars or large stars. I would say small stars, medium, or low mass stars. Large stars are what I call high mass stars. And you can see that elements all the way up to, roughly speaking, iron can be produced in stars. Now, there is a little bit of copper, zinc, but those are not sustained reactions. Okay? You might have a one-off every once in a while, but it's not a sustained reaction. Most of the other high elements, you notice marked with the dollar sign, happen during the supernova process, when the electrons and protons fuse together to form the neutrons, and the rest of the material is ejected out into space. That ejected material, the 80%, sometimes undergoes a fusion process to form things like gold or platinum or silver or tin or iodine and xenon and lead. It's not by accident that some of these higher periodic table elements are more rare. It's because the process that produces them is not as common. It's harder to produce high mass stars, which means supernovae are not as common, which means you're not going to get these elements as often. Pretty cool, huh? Let's focus in on this for a moment. We've got a couple minutes here, bear with me, and then we're almost done. Let's focus in on iron and silicon. And the reason I'm going to focus on this is because it relates to a lab question that I asked you weeks ago. This. At one point during your lab, I believe it was the spectroscopy lab, I said, here is the spectra of the sun. And I don't have it displayed here, but I gave you a table of various elements and their wavelengths. And you should have noticed in the spectra of the sun that you had a strong iron line or a strong silicon line. And right away, that tells you something about the generation of our sun. Here it is. Can a medium mass star like our sun form iron through the fusion process? No, it cannot. It is a medium mass star. It won't be able to go farther than carbon. So then the question becomes, how does our sun have iron in it? It must be that the cloud of gas from which our sun has formed originally contained iron in it. Well, where did that iron come from? The iron in the cloud of gas from which our sun formed. It must have come from the explosion of a prior star. Incidentally, the same thing would go with our planet. The iron that's in our core of our planet could not have been produced by our sun. It must have come from somewhere else. It must have come from a star that has exploded in the past. Now, I'm saying it must have. I should say that's our model. We have a model that describes how stars evolve, including how they could produce different elements through the fusion process. We also have an idea about how those stars could expand or throw that elements back out into space for the process to reoccur again. Now, what we would say, I've been using the term generation, but what we would say is that our sun is a population 1 star. Population 1 stars are stars that are dirty. In other words, they contain more elements than just hydrogen and maybe some helium. Okay. So if it just contains hydrogen and helium, it is what we call a population 2 star. It is a star that is formed from a clean cloud of gas. We generally think of these as being older stars, stars that have been around longer than population 1 stars. They have not been contaminated, population 2. Last bit that I have to show you, and then we'll call it quits for the day. What happens if you're above 7 solar masses? And this ties us back to the video or the picture at the beginning. What you are looking at is the first ever image taken of a black hole. This is the black hole at the center of M87. The reason that we chose it is because it is a supermassive black hole. Right here, probably roughly the size of my pointer, is the size of Neptune's orbit. This black hole is a monster. It is so big that we can image it here from Earth, even though it's hundreds of millions of light years away. The video that I'll post a couple links here for you, but the videos that I'll post, it's like trying to read a CD located on the moon, or conversely, trying to distinguish the dimples of a golf ball that's sitting in San Francisco while you're in Bangor, Maine. So you're trying to see the difference of 2 dimples on a golf ball across the United States. It is amazing that we can even get this picture. But the same idea holds. What happens is that if you're greater than 7 solar masses, you start collapsing. And you collapse and you form a neutron star. You push all the electrons into the protons and you form a neutron star. And then you keep collapsing. And then you break physics. I shouldn't say you break physics. We still have an idea that models up to the formation of a black hole. But after that, we don't know for sure. Everything's a bit speculative. We have to rely on our models, but nothing's quite known for sure after that. That's why this is so exciting. Einstein predicted the existence of these in 1915. It wasn't until 1919, 100 years later, that we had the technology and the ability to get this picture. I'll let you ponder on that for right now. Thanks for your attention. I'll see you next time.